recent progress in the theory of constant mean curves as surface. Thank you.
Right, and I just want to mention ahead of time, most of this work is work I've been involved with. Some of it with Harold Rosenberg, some of it with Joaquin, some of it with Joaquin, Antonio Ross, and I said Joaquin Perez, Antonio Ross, and myself, and Giuseppe Tenaglia. That's most of where the work's coming from. And there are lots of pretty pictures. The talk's only 40 minutes long, so there are some proofs, hopefully, but not too many proofs. Mostly just telling you about what's happening, what's happened, some improvements on previous results, things like that. Okay, so we start off in R3. Not all my talk's in R3, but certainly a good part of it has to do with surfaces in R3. And you have the Gauss map, and you have its derivative, which gives rise to the shape operator, or the second fundamental form. So you watch how the normal vector changes on the surface. And anyway, so that's a symmetric, you can think of the symmetric transformation, so you can diagonalize it with an orthonormal set of eigenvectors and with eigenvalues. The eigenvalues are kappa 1, kappa 2. Those are called the principal curvatures. And you do this at each point. You get functions. For example, taking the determinant of this family of matrices over the surfaces, you get the Gaussian curvature function. You have the mean curvature function, which is the average of the it's a trace divided by 2, and which is the average of the normal curvature. And you have the norm of the second fundamental form. So those are all key invariants in my talk. Okay. Norm of the second fundamental form being big means the surface curves a lot. If it looks like kind of like a plane locally, then the norm of the second fundamental form is small. Okay, and we have a function. We have a relationship between those functions. Okay. All right. So the main part of my talk is about CMC surfaces, and I'm going to call those H surfaces when you fix the mean curvature. So they're constant mean curvature surfaces. Okay. So an H surface, maybe a 1 surface, would be a surface of constant mean curvature 1. So that's a standard notation. Green lots of times means mean curvature. So a 0 surface would be a minimal surface. Okay, so so we have, that's the definition of H surface, and it satisfies a nice equivalent variational property, which is that it's a critical point to the area functional under compactly supported variations that infinitesimally preserve volume. So if you fix the boundary and you move the surface, so on one side, think of moving on one side at a rate that's sort of equal to the other side, then the volume infinitesimally, the algebraic volume doesn't change. So you have the sides of the surface. Okay. So so we have our classical examples. The classical examples are going to be very important in my talk. To what extent these surfaces are unique in some kind of sense. So we have the sphere, we have the cylinder, and we have Delaunay's surface. Okay, those are surface of revolution. These are the ones of revolution right here. Well, that's also a surface of revolution. So this is, if you want, the examples of revolution that are embedded. Another word for Delaunay's surfaces are unduloids. Okay, so specializing to the case H equals 0, we call those surfaces minimal surfaces. And they have the property that you can allow the variations to be not necessarily volume preserving. Any variation, for example, a positive variation. You have an oriented surface, you can move it away from itself on one side. That certainly doesn't preserve the algebraic volume, but it's fine. Okay. And our sort of famous examples are the catenoid and the helicoid. And we have physical properties for these solutions. We have soap films on wires. Those are minimal surfaces. So surface tension produces least energy, or local minimums for the energy functional for the physical surface. And it turns out that minimizing energy is like minimizing area. So they're somehow almost like proportional when you conformally parameterize the surface, which you can always do. So anyway, so we get soap films. Now, if you took that soap film on the first one and you just kind of blow air on one side of it, so the pressure difference is constant. So maybe on one side where you're blowing air at a certain pressure, the constant difference in the pressure, you end up making a constant mean curvature surface. So that's another reason why we see these things in nature. Okay, so the first main problem, you can think of this as somehow anyways, it's a problem which you can understand, and it motivates most of the rest of my talk. So is the round sphere the only complete, simply connected surface embedded in R3 with non-zero constant mean curvature? Okay, so if you're looking for a simply connected H surface that's complete and embedded in R3, do there exist any where H is positive and you're not compact? Can you put a plane in R3 with constant mean curvature that's not zero? We certainly have cylinders, but they aren't simply connected. And you can, in fact, conformally map the complex plane into R3. And with constant mean curvature, say 1. And, but nobody ever found an embedded one. Okay? So those are the things. And the answer to the question is, are these the only examples? And the answer is yes. So this is essentially saying there are no planes that are complete embedded with non-zero constant mean curvature. All right, so the answer is yes, and we're going to see various reasons why. So we want to get some intuition about the behavior of the surfaces. So this first part of my talk is what is the intuition? What is happening in the internal structure of simply connected minimal surfaces? So that's the theorem. Round spheres are the only examples of complete embedded non-zero mean curvature. And very important to understand, when the surface is properly embedded, so for example, it has finite area inside of balls, that's essentially equivalent to being properly embedded, then this was proved about 30 years ago, okay, by myself, right when I took my present job in Amherst, Massachusetts, right before I came there, okay. I think I actually even mentioned this. I gave a talk at the plenary lectures at the International Congress at Berkeley. So right before I went there, I figured out this result. But it's for properly embedded, one question. And ever since then, I've been trying to say, is this result true if you just say complete and embedded? It's a question that's been on my mind and probably some other people's mind for many, many years. Okay, and so when you go from properly embedded to complete and embedded, it's not an easy question. So in fact, we have in 2001, first we had this result that Harold Rosenberg and I proved, that the helicoid is the only complete properly embedded plane in R3 that's minimal. So you have the plane and you have a helicoid. Those are the only simply connected minimal examples that are properly embedded. But then you have this beautiful result of Colli-Mancosi that say for minimal surfaces of finite topology, complete and embedded is equivalent to properly embedded. So we could apply our result and understand this question for minimal surfaces. So the only examples that are minimal are a plane and a helicoid, and you're always properly embedded, so that's good. And you have the theorem above, which solves the case for spheres. So it's a complete understanding. There are three examples, basically. All right. So let's try to understand where is this result coming from in a sort of a bigger context. So if you look at a complete, connected, embedded H surface in R3, so we're looking at one of these surfaces, then we have some properties. If it has positive injectivity radius, it is properly embedded. So for example, in the previous problem, is a plane of constant mean curvature have positive injectivity radius? Not an easy question. Not an easy question. So we have to understand things better. But when you have finite topology, it's a non-trivial result that you have positive injectivity radius when you're not minimal. When you're minimal, it's easy to prove. When you're not minimal, not so easy to prove. But anyway, now we have another way of seeing why that previous theorem is true. So a plane, constant mean curvature complete embedded in R3 is going to have positive injectivity radius. If it has positive injectivity radius, it will be properly embedded. And here we have something that's peculiar to constant mean curvature bigger than 0. So the norm of the, if you fix, the result is the norm of the second fundamental form of the surface, it's a function, is bounded if and only if the injectivity radius is positive. Those are equivalent properties. Okay? And if you fix H, the bound on the norm of the second fundamental form only depends on the value of H. Okay? And basically, by scaling, you can do homotheties. You can see it really depends on estimate for constant mean curvature 1. Okay, so this estimate is uniform there. Okay, it only depends on the value of the injectivity radius. Okay, so when H is 0, then we have items 1 and 2 were proved by myself and Harold Rosenberg, and we proved a fairly general result of which, say, number 2 was a number 1 was a corollary. Okay, but our work was also based. My work with Harold Rosenberg was also based on this big theorem of Kolde-Minicozzi about 5 years ago in the Annals. They proved that if you had finite topology minimal surface, then and complete and embedded, then you are always properly embedded. Okay, so there are techniques in there, and some of those techniques are also used to prove these results here. And Harold and I used those to prove, for example, number 1. Okay, so to what extent is number 3 true in 3 manifolds? So, for example, if you take a closed Riemannian 3 manifold, compact, without boundary, and inside that you look for, and you put a Riemannian metric on it, do you have 3 true? And the answer is yes. So for closed 3 manifolds, we still have 3 true. And again, you have an estimate that only depends on the injectivity radius. The norm of the second fundamental form only depends on the injectivity radius. Also holds for other manifolds, but anyway. Okay. So one of the stranger results is this one. It says if you have a constant mean curvature disk, so let's think positive. I'm not going to tell us much for minimal. And say constant mean curvature 1 in R3. Then does there exist an estimate, an upper estimate on its radius? Okay, in other words, can points be very, very far from the boundary? So if you take when I say H disk, I'm always thinking compact. So if you take a compact H disk embedded in R3, and H is, say, 1, is there always a bound from above to the distance to the boundary? So if you take a point in the interior, you look at the intrinsic distance, look at curves going to the boundary, is there a bound? And that's called a radius. So the soup of these, the maximum of the distance to the boundary is radius. And this says that there's a number bigger than or equal to pi. Pi might be the sharp number. Maybe pi works. It has to be at least pi. But you have this estimate on the radius of any H disk. Notice when H is 0, it's not very interesting and says that, compact disk has finite radius, of course. Anyway, that's the result. Kind of surprising, because you can have very complicated compact disks. You can make compact disks which are going almost like dense, and they're just all over the place. They're winding around, but even though they're kind of all over the place, every point is not very far from the boundary. So anyway, okay. So immediate corollary of that result is that if you take a plane in R3, you can't. Okay, so if you take a complete, simply connected H surface embedded in R3 with H bigger than 0, then it's a round sphere. I'm using here, of course, Hopf's result. I just need to know it's a sphere. You could use Alexandrov, or you could use Hopf and then prove it's round. So the question is it compact? Is it a compact sphere? And the reason for this being true, if it were not a sphere, it would have to be topologically a plane. So you have a Riemannian plane. You can parameterize it by the plane in R3 by round disks and just map that in there. Then you have a compact exhaustion by disks. The plane has a compact exhaustion by disks. And eventually, those disks have to have arbitrarily large radius. Right? Okay. Because the boundaries go to infinity. Okay, so that's immediate consequence. And then we have this very, very, very useful, it's probably going to be a very key tool in the future for understanding complete locally homogeneous 3 manifolds. So this says that if you pick an epsilon and an H naught bigger than 0, so H naught is going to be a lower bound for mean curvature, epsilon is somehow going to measure the distance to the boundary. So think of epsilon as being small, or maybe it's big. But anyway, kind of think more on the direction that it's small. And you fix a complete locally homogeneous three-manifold. Okay? Then there exists a constant such that whenever you look at an embedded H-disk in X, okay, but the mean curvature is at least H naught, then you have a curvature estimate away from the boundary. So if you take any point on that disk and you're intrinsically at least epsilon away from the boundary, it's just kind of like for stable surface. You're at least some distance from the boundary, then you have a bound in the norm of the second fundamental form. Okay, and I'm not going to go over the proof, but anyway. Okay, so what are key techniques? There's some very technical sort of results that come out of Coulomb-Nicosi theory that are applicable to understanding these problems. So one of the first ones, famous ones, that come from minimal disk is the one-sided curvature estimate. So this says that there was work done by Coulomb-Nicosi for minimal disks, and this says the same result, or not exactly the same result, but a similar result is true for constant mean curvature disks. Okay, so you want to look at, in other words, if you have a disk, this blue curve is supposed to be our disk, and it's and you're in a ball of radius r. This estimate doesn't depend upon the mean curvature. You're in a ball of radius r. There's a very, very small universal number epsilon, such that if you look at the ball of radius epsilon r, and you look at the part of the surface that goes through that epsilon ball, you assume the boundary doesn't go into that upper half ball. So the boundary, you can see, lies outside of the upper half ball, and the disk is embedded. Then, nearby the origin, in that ball of radius epsilon r, it's graphical. Well, if it's graphical, it has curvature estimates. It's stable, and stable has curvature estimates. So it looks graphical near the origin. So that's a sort of universal sort of result. It's also true in some contexts in manifolds, like locally homogeneous manifolds. Okay, so here's something I've actually been working recently with Giuseppe, very recently, and we were interested in this chord arc estimate. So what's the relation between intrinsic and extrinsic distances? There's some kind of proportionality between, it compares those distances. And if you think about various things like helicoids where you put points, then you can see that there are restrictions on what happens. So this says that if you fix two positive numbers, think of very small, and then there exists a constant which is very big, and such that whenever capital R, that's going to be a radius, is bigger than some smaller radius, which is positive. So you want to pick numbers that have that property. Okay? And you take any surface, sigma, which is embedded H-disk. It could be minimal, it could be not minimal. So this is also even a new result for minimal. So minimal, or anyway, an H-disk. And this disk has a certain property. It passes through the origin. Okay, that's the first property. We want that the intrinsic ball in the surface at the origin of radius C capital R doesn't hit the boundary. That ball does not hit the boundary of your H-disk. Okay? And we want to assume some property about the second fundamental form being non-trivial. So for example, if you have non-zero constant mean curvature, you always have the second fundamental form is always at least something. So you want to say that in the ball of radius R naught on the surface, the norm of the second fundamental form is at least something. And at least something is 1 over R naught. Okay? Then you have a chord arc estimate for the intrinsic distance from X to the origin. So X is in your, but you restrict the points in the ball of radius R. So you think of this capital R being fairly large. So there's a way of comparing intrinsic and extrinsic distances. And unfortunately, I have this epsilon 1 here and epsilon 2, but think of them as being very small. It says the intrinsic distance is less than or equal to, like the square root of 2 times the norm of X plus 2 times R naught. Okay? Whenever I'm in the ball of radius capital R. Okay, so this is somehow a universal estimate, and it's sharp because those numbers square root of 2 and 2 can't be improved. You take any number less than the square root of 2 or less than 2, then when epsilon and 2 are sufficiently small, I can find a counterexample to that formula. So it's sharp. That's exactly what happens. Okay. What I don't know, I tried to do, but I couldn't figure it out, is to show that that constant doesn't depend upon epsilon 1 and epsilon 2. Maybe it's universal. So for example, just restricting a little bit, in the case epsilon 1 and epsilon 2 is 1/2, we got an easier to remember formula. So 1/3 of the intrinsic distance is less than or equal to the extrinsic distance to the origin plus this little constant R naught. Okay? So this generalizes a sort of a similar statement for minimal surfaces by Coulomb-Nicosi. They don't have something sharp. This is sharp, essentially sharp. Anyway, and it immediately implies properness for complete simply connected H surfaces. Okay? Okay, so as I go away from the origin, I have to, this is going to become big, right? But therefore, the extrinsic distance has to be big as well. So improper. Okay. So this leads us to a bunch of questions related to what's called the Claudio problems, a really essential problem in the subject, and even in the manifold setting. There are lots of questions. Anyway, so this is sort of an amazing conjecture if it's true. And it says, take a look at this particular solid domain. It's like a G-hole donut, but it's got an infinite number of handles. And these handles get smaller and smaller, and they converge down to a particular point on the boundary of the domain. So this is an infinite genus handle body in R3. One singular point on the boundary. It's not smooth at the boundary. Then we conjecture that if you take any open surface with compact boundary, maybe the boundary's empty, okay? So then it properly minimally embeds into this domain if and only if every end of that surface has infinite genus. Okay? If and only if it emits a complete embedded injective immersion into say a ball of some radius, bounded immersion. So that's the claim. Okay. And you, in general, for example, if you took a non-orientable surface, such that every end is non-orientable, and you had an uncountable number of ends, that's a very complicated surface. That will satisfy the hypothesis here, and therefore should map into here. On the other hand, it will not map into any smooth bounded domain properly. Okay, so there's some interesting things. You really need singularities, at least one singularity. Okay. All right, so this leads us to a very fundamental question, which we unfortunately still struggling with. Haki and I have been working on this especially a long time. Okay, so but it's a great conjecture. It's probably provable. It's maybe the most interesting question about minimal surfaces in R3. So it says complete, connected, embedded H surface in R3 of finite genus and compact boundary, if you want to generalize. Okay, compact boundary doesn't have anything to do with the problem. Then there exists a constant that depends on that surface such that in balls of a radius at least 1, you have an estimate on the area. It's very interesting. Okay, it somehow can't, its area growth is at most cubical. Okay, and there's a case where we know how to do that. Okay, so the embedded Claudio problem says for finite genus is basically that conjecture, but we have this partial result that says if in the minimal case, if you have a complete embedded zero surface of finite genus, then the surface is proper if and only if it has a countable number of ends. Okay? And when it's proper, we also know it satisfies that equation up there. It has cubical, and most cubical volume growth. I didn't state that, but that's, so in this case of a countable number of ends and minimal, we know how to prove that. Giuseppe and I are more working on the case of Positman curvature, And I'm pretty sure we'll actually be able to prove that case. So positive mean curvature will probably be able to prove this estimate. Notice that there are properly embedded genus 0 surfaces in R3 with constant mean curvature 1 with an uncountable number of n's. So the situation is different for minimal. And you can make the second fundamental form be bounded or not. You can have unbounded. You can have every end have unbounded second fundamental form. So you can have very complicated examples, but the claim is you still have an area estimate. And an area estimate implies properness. Okay, so I've been talking about genus 0 surfaces of infinite topology. We have these beautiful examples of Riemann. So Riemann comes from a deformation of the catenoid. So you can take a catenoid soap film, you slide the top circle sideways a little bit, you get a soap film. Turns out that soap film is foliated by round circles in parallel planes, in horizontal planes in this picture. And that's an analytic property. At some point, the circles have infinite radius. They come straight lines, and you can rotate around the straight line. So here's a beautiful picture by Matthias Weber. It's one of my favorite pictures that he made. Unfortunately, I think this is from a scanned version. He made it when I was visiting him, and I don't know what ever happened. But anyway, I don't know. I don't have the actual PDF file of the picture, so it's not a perfect picture. But anyway, so this is a picture of this Riemann staircase, okay? And there's a one-parameter family of them. As you move the circles, there's one parameter family. And you can imagine just walking up this flight of stairs. Now, we have these sort of look like circles this way. Those are not actually circles, but the surface becomes asymptotic to a plane at those heights. So it's like an infinite stack of planes joined by these sort of catenoidal tubes. And so here's one of my photographs. I should say very few of these pictures I made myself. So the previous one, this one, not the previous one, but anyway, this one I actually did by hand. So classification. What are the properly embedded minimal surfaces of genus 0 in R3? Properly embedded. Notice the word proper because we don't know complete implies proper yet. So these are the examples. We have the catenoid, we have the helicoid, and we have the moduli space of Riemann examples, and somehow they, in a natural way, limit to the helicoid, or in one direction they limit to the catenoid. So that's a very pretty result. Very useful to know this classification result for doing other problems. For example, problems like this one. So in a 3 torus, in a flat 3 torus, you can actually put, if you take any genus bigger than 3, or genus 1, there's no bound on the area of minimal surfaces. You can take a sequence of, in my thesis, you can take a sequence of genus 0 minimal surfaces embedded in a flat 3 torus. And they converge to a foliation of the 3 torus. You have a sequence of them. They converge to a foliation of the 3 torus, and the convergence is smooth outside of 2 points. Okay? So you can extend across that. So you can have area go to infinity. And Frazé did this in general for any genus bigger than 2. Okay? And these things come up in nature. You could ask, well, could the area be big if I solve some kind of physical problem? Evidently not. So anyway, but we do have area estimates when the mean curvature is positive. And I've still been thinking about this recently. Anyway, so we have the area can grow at most linearly with the genus by a formula like this. And you can also try to do similar things in a manifold setting. Now, it turns out for H positive, it's not too hard to prove. You have a flat 3 torus, you take a constant mean curvature surface compact embedded in it. Positive mean curvature, it turns out it always separates. So this result is very closely related to trying to understand the similar problem in homology 3 spheres. And here, when H is positive, we get separation. In homology 3 sphere, every closed surface separates. Okay. So now I'm going to go from what I've been talking about to the situation of foliations. Okay. And CMC foliation. So what is a CMC foliation? It's a foliation, all right, 2-dimensional. We're thinking of 3-manifold setting foliation by surfaces, okay? And we want the foliation to be transversely oriented, so it has a normal field, so we can calculate the mean curvature as a function with a sign. And we have the mean curvature function. We want to be constant along the leaves of the foliation. So each leaf of the foliation has constant mean curvature. And we have this quite deep result that says if you have a weak CMC foliation of a punctured Riemannian ball, okay, and weak is just generalizing. It's, if you have a weak, it has some kind of singular structure, but it's pretty, on the mean convex side of any leaf, it looks like a foliation. But the leaves can somehow touch on the other side. So we'll see examples in a minute. But anyway, so in particular, you have bounded second fundamental form. That's a property. So if you have and it turns out every foliation is a weak foliation. So anyway, so you always extend across the origin. You can always extend, for example, you can always extend across the point P. In particular, you always have bounded second fundamental form. So it's really it's related to a curvature estimate. In particular, you get a curvature estimate. Okay, so all right. And this says you extend across the ball if and only if the mean curvature function on the ball is bounded. Right? Certainly can't extend across it if the mean curvature the leaves going to infinity near the point. Think of concentric spheres in R3. You can't extend that foliation across the origin. The mean curvature function is not bounded. Okay. And the key ingredients are curvature estimates for CMC foliations and local removal singularity theorems for weak, what are called weak H laminations, where you fix the mean curvature. And we have this very nice application of these ideas. What are the CMC foliations of R3? Where you might allow singularities, a countable number of singularities, like 2 in this picture. This goes back to something Harold motivated me to work on back in 1986, I guess, 85, 86, which was what are the CMC foliations of R3? And so back in 1986, I proved that the only ones are parallel planes. You can't have leaves of non-zero constant mean curvature. And this is somehow generalizing that. If you allow singularities, we have lots of interesting examples, then it's saying that when you have a countable, possibly a countable set of singularities, then in fact, all the leaves are contained in spheres, round spheres, or planes. Okay. All right, and when you're looking at closed Riemannian 3 manifolds, you could ask similar questions. Do you have some kind of result about extending things? Anyway, if you have a CMC foliation of a closed 3 manifold, I should have said orientable. Oh, it says orientable. Orientable, non-empty set of singularities, say countable again, then you must be the 3-sphere. That's interesting. And certainly have lots of examples on the 3-sphere. So we have a lot of CMC foliations of the 3-sphere, outside of, say, 1 or 2 points. Okay. And you can kind of try to generalize this question. You can say, how about if I have an N manifold? Do I have a CMC foliation? Well, certainly, if you have a CMC foliation, you have a non-zero vector field. You have the normal vector field of the foliation. And so the order characteristic must be 0. And in fact, we can make this foliation to have the mean curvature change sign on the leaves. Okay? And in the case of the manifold is orientable. This was proved by Oshikiri. And the non-orientable case is somewhat different, more difficult. Okay, anyway. And our proof is just independent of whatever he did. So, and let me just show you a picture. I think I'm not going to have much time. So, so this is the surface of revolution, say periodic, like sines and cosines mentioned defining. Well, certainly foliated by curves of constant geodesic curvature, right? So there's one in dimension 2 where the mean curvature changes sign. And it also has some symmetry. So if you can reflect in a plane and translate, that's called a glide reflection. And if I divide out by that glide reflection, I get a CMC foliation of a Klein bottle or a torus, depending upon how I do it. And I think I won't have time to talk about this slide. But you can do the similar kind of thing in higher dimensions. One thing that's nice about what Haki and I did is that when you take this N manifold with order characteristic 0, we create a foliation by Thurston's result, a transversely oriented foliation. Not everybody knows that result. But anyway, transversely oriented foliation. You kind of create a minimal metric. You do something to the foliation. You modify it by a surgery, sort of surgery. That's called turbulization. And you do some things, and eventually we create this foliation. One of the neat things about what we do is if you take any region, which is when we make this foliation and the metric, any region where you look at the leaves of positive mean curvature, you take those regions, they're all like solid donuts, n disks, n minus 1 disk cross circles, and you go to the universal cover of them, those for each dimension n, those manifolds are fixed. So the part that's not minimal is completely sort of understood if you go to the universal cover. Fixed metric, fixed foliation. Okay, so I have time to talk about this a little bit. Yeah, 5 minutes. Okay, so we have some important invariants. Both of these invariants are very important in the theory of CMC surfaces, or H surfaces in manifolds, especially in homogeneous manifolds. So we have the Cheeger constant. We have something called the critical mean curvature. I think they're filming this, so we can read this at more leisure. It's somehow, anyway, critical mean curvature is the infimum. On each immersed closed surface, you look at the mean curvature function. You take its absolute value, its norm, so it's like a non-negative. You take its maximum value, and you take the infimum over all surfaces. It kind of looks like a minimax, but it's really nothing like a minimax question anyway. It's a number associated to the manifold. And it's called the critical mean curvature. And one of the results that we really needed for doing solving other problems, like classification questions, was this, this equality. Remember, the mean curvature is the average normal curvature. If you just defined it to be so the average, the trace is the second fundamental form, then this number is the same number as the Cheeger constant. Okay, so very nice. And one reason it's nice is it's relatively easy to calculate the Cheeger constant. Why? This is for simply connected homogeneous 3 manifolds. So the Cheeger constant turns out to be relatively easy to calculate as long as you're not a particular Lie group with a left invariant matrix, which is SL2R tilde, the universal cover of the special linear group, real special linear group, dimension 2. Otherwise, this number is fairly easy to calculate from the geometry of the ambient manifold. Otherwise, it's probably doable, but it's like you have to solve it ODE or something. But anyway, whereas the critical mean curvature, who knows? It's very difficult to calculate. And how do you relate these numbers? We produce in our simply connected Y, we produce foliations where you have the critical mean curvature as the mean curvature of all the leaves. Okay? And we use these foliations. There's a lot of classification going in the background here, so we have to know what all the Y's are and all that kind of stuff. So, and notice the Cheeger constant is related to solving the isoperimetric problem. So if you take a sequence of isoperimetric domains whose volume is going to infinity, and then you get some inequalities. You have the critical mean curvature, of course, bigger and equal to h of y, right? I mean the mean curvature of the boundary. The mean curvature of the boundary is, it's a surface of constant mean curvature. So it's something you can plug into h of y. It's a number that's in that set of infimums. So that's nothing to do there. What's interesting is the mean curvature of the boundary actually goes to the critical mean curvature of the space. And like I said, to do that, you need these h of y's foliations. Okay, that's a very brief idea. But there are other things you can do here. So let me just put these 3 results up here together, because I'm running out of time. What are the simply connected homogeneous 3 manifolds? So you have homogeneous 3 manifold, you go to the universal cover. What are those universal covers? Well, you're either a metric Lie group, which means a Lie group, 3-dimensional Lie group with a left invariant metric, or you're not. And if you're not, you're S2 cross R. So a sphere of some radius or Gaussian curvature, anyway, cross R. Those are the only 2 examples. And we have this very nice problem called the Hopf uniqueness question. To what extent are constant mean curvature spheres unique in a homogeneous manifold? If you have 2 of them the same mean curvature, are they congruent? Is there an intrinsic isometry that maps one to the other one? That's the question. And in the case of S2 cross R, one can solve this problem, and one can actually prove it. And but there, really strongly one uses the classification that all constant mean curvature spheres are spheres of revolution. Okay. All right. Okay. So here's what happens in general. So we understand S2 cross R for constant mean curvature spheres. What are the other cases? Other cases are simply connected metrically groups, because you can always lift spheres to the universal cover. So then we have this result. If you're you have sort of different cases. One case, you're diffeomorphic to the R3. Then it turns out, after congruences, every constant mean curvature sphere that's oriented has associated to a point of symmetry. This is like a center of mass for that sphere. The symmetries of the point of symmetry create ambient symmetries on the surface. Okay? And if you sort of fix that point to be a particular point, like the density element in the Lie group, then you get this one-parameter family. That's what the theorem says. You have a one-parameter family of constant mean curvature spheres, and they are parameterized by their mean curvature. Okay, so if you're the three-sphere situation, it's different. You have a constant mean curvature sphere for every possible value of the mean curvature. And actually, in this case, it's very natural to think of oriented spheres and also allow the mean curvature to be negative. So in this case, it's also it's useful to think about, you got to the minimal one, you just keep going. So the mean curvature varies, and it just goes from being 0 to being negative. So it's kind of useful for doing some things. In the case of the three-sphere, we have a bound on the areas. Another key property is that all the spheres bound immersed balls. So they're all Alexander embedded, index 1 with nullity 3. So this is a simple idea here. If you go back to the second bullet, when you're diffeomorphic to S3, remember I kind of say fix the identity element. I have that point be the center of symmetry of my sphere, and I get this one-parameter family of spheres. So when I get to minimal, h equal to 0, I am right. 1 minute. Okay, better go. Okay, let me just tell you the steps of the proof real briefly. So one studies the moduli space of index 1 spheres. So let sigma in this to be a fixed constant mean curvature sphere of index 1. First thing you notice is you can apply Chang's theorem, and you get that this surface has nullity 3, coming from the right invariant vector fields. You have by the implicit, once you have that result, you have an implicit function theorem. It says that the moduli space is one-dimensional. Given an example, you can deform the mean curvature in a one-parameter family. So you have this one-dimensional moduli space. We have step 2 is very, very important, very interesting. It says that the Gauss map has a degree 1 diffeomorphism. So this involves representation theorems. And it's not I don't know an easy proof of step 2. Step 3, once you have that result, you have curvature estimates. A surface of very big, fixed mean curvature, a very big curvature, looks like a minimal surface when you rescale. A minimal surface has degree -1 for its Gauss map. It's got negative Gaussian curvature. So it's very easy to see. Step 3 is kind of trivial. This is where really the hard work is. If you're SU2, you prove you have bound on the areas of all constant mean curvature spheres as a uniform estimate. And if you're not SU2, once you're a little bit bigger, delta bigger than the critical mean curvature, you have area estimates. So once you're a little bit bigger than, you have at least some kind of space above the critical mean curvature, then you have area estimates. So this is really, probably Hawking said I should say it's work in progress. This is very long. This is very, very difficult. It involves like complicated mathematics. But anyway, for me, I think it's fine. But anyway, we're still writing it up. It's over 100. Just this part is about 100 and some pages. and there are no H-spheres. So from that, immediately you get understanding the moduli space, because you have a constant mean curvature sphere. You can deform it up the mean curvature till it's really got huge mean curvature. There you get uniqueness, so you can understand that. And using the Gauss map as a diffeomorphism, if you have something different than, it's not a left translation of that sigma, some other constant mean curvature surface sphere, then you can create a quadratic differential with a non-zero complex valued quadratic differential, and then using the order characteristics when it gets a contradiction. So if you have a constant mean curvature 1 sphere, you have, by the top bullet, there's a constant mean curvature index 1, 1, and then you apply this result, so you know it's a left translation. Anyway, from that, the rest of the result follows. Yeah. Let me just put it up here so people can see it. Okay, that's it.